Welcome everyone to the second talk in the Gordon Lecture Series by Peter Sarnak. The third talk is going to be on Thursday, same room at 11 o'clock. And thanks, Peter. So we're talking about prescribing the spectra of locally uniform geometry.
Thank you very much. It's actually warmer than I thought. Rather musty. Okay, thank you, and thanks for the opportunity to continue with this topic. I guess I can write here if I need to. So the first lecture was about this problem, which I'll quickly review, in the case of Euclidean space. And in that case, everything really boiled down to the geometry of numbers. And today I'm going to talk about the non-Euclidean case, where it does not reduce to the same kind of geometry of numbers, but rather to something quite different and much. And it's actually in this context that seemed to me this definition should be made of the base note spectrum. So let me explain that. But before I just review, for maybe some of you weren't here in the first lecture, that the general problem is we have a locally uniform, we have a globally symmetric space or global space, and then we divide it to make locally uniform geometries. It could even be a Brouwer-Titz building. And we vary over all the local geometries, asking what spectrum we can create or what gaps in the spectrum that we can ensure for some linear differential operator or a Hecker-like operator that's acting on the global space and relative to which it preserves the motions of the geometry. So the key is this definition, and I'm very interested in this rigidity issue, as it will become clear in this lecture too. So I'll just again review the definition. So this lecture is about the base note. The third lecture will be about prescribing gaps in other parts of the spectrum, and in fact, the order of these lectures is a little different to the order of the other talks. So the talk later by Boris and by Alex Smith are more connected to making gaps in other parts of zeros of zeta functions of curves when the topology gets complicated. And I think I'm not sure what you'll say, but I know what he will say roughly. So the case that's relevant here is going to be hyperbolic space. We have this, and it's back to the base note. We look at the smallest eigenvalue in absolute value. As we vary over the family, we get a set of real numbers. We close that set. For those of you who were in the earlier talk today, in the Markov case, you don't have to close the set. It's already closed. But if the set of geometries, and I insist on allowing myself the freedom of taking a subset of the geometries, so as to see the impact of imposing conditions like arithmeticity or number theory, how that might impact the nature of the spectrum. So once we impose a subset F which might be countable, for example, then we're not asking to write down the eigenvalues of everything. That's too ambitious. The closure of the set is what's important, and that's the definition of the base note. And throughout, I will refer to the discrete part of the spectrum and the limit points. So the limit points, so it's a subset of, it's a bound, in this case when we get differential operators, it's a subset, a closed subset of 0 infinity. And the discrete points and the limit points, or the limit points, as you define normally in topology. The notion of rigidity, I was discussing that with Uri and Omri just a moment ago. It might be that in some situations where the spectrum wants to go to maybe a finite number of points, and maybe one should promote rigid not just to have a single limit point. But in today's lecture, rigid will mean there's only one limit point. Everything goes to that one point. Okay, so I'm going to talk about the hyperbolic case, but just to remind you, for those who were here last time, and for those who've never seen it, the richest case I've ever seen is the Markov spectrum. That is the case that if we reproduce anywhere, we'd be very happy. It's clear that in the geometry of numbers, that what Mahler, Davenport, Mordell were looking for was the analog of Markov in higher dimensions. They always refer to this Markov paper as kind of the example and the motivation for what they do. All right, so yeah.
Too fast.
No, that was last time. That was review. See, you were sleeping last time. Okay, let me start from afresh. So what are the geometries, firstly? So today we're not interested in Euclidean geometry. We're going to be interested in the hyperbolic geometry, which is the upper half plane. The symmetry group is PSL2R, acts by Mobius transformation, linear fractional, preserves the metric with a hyperbolic metric, constant curvature minus 1 metric. To make a locally uniform, everything you think of as compact quotient, so to make a locally uniform geometry, I take a discrete subgroup. For certain purposes, let's allow finite volume, and the quotient is a hyperbolic orbifold. I insist on allowing singularities, because that will allow for clean answers. Similarly, if you start with hyperbolic 3 space, there are different models for hyperbolic 3 space, but if you take the upper half space and you write down the action, which is a little more complicated than this linear fractional, it looks very nice if you use quaternions, then you get the group of motions is PSL2C, and if you have a discrete subgroup of PSL2C and you form the quotient, that finite volume or compact, you get a hyperbolic 3 orbifold. So we'll be, our family of locally uniform geometries will be these two today, and there will be discrete ones next time. All right, so what kind of operator are we going to look at here? So we're going to look at operators which are a little friendlier than the ones we were looking at this morning, which were indefinite and where all sorts of weird stuff comes. We'll look at Laplacians, but you'll see the spectrum is really challenging. So just my notation, hyperbolic D denotes so D is going to be just 2 and 3 in this lecture. So hyperbolic plane or hyperbolic 3 space, or all the hyperbolic surfaces, orbifolds, and a hyperbolic 3 manifold orbifolds. Laplacian is going to be the Laplacian on functions. It's always what I've always liked, but we will also allow Laplacian on forms and on tensors. That's where it gets really interesting from some points of view, connected with topology. So the spectrum of the Laplacian, suppose we're in a compact quotient, let's assume it's compact quotient, then we look at the Hilbert space of square integrable functions on this quotient, we look at this operator, which has got a self-adjoint extension, we don't go into technicalities, it's got a discrete spectrum, the constant function is annihilated, I'm assuming all of my orbifolds are connected, so 0 is the smallest eigenvalue, and this base note is lambda 1, which has been much studied for many, many years for many different reasons. All right, so if I have a subset of hyperbolic surfaces or hyperbolic 3 manifolds, I review the definition. The base note spectrum of the family is the set of all values assumed by the base note. So it's what can you make the base note equal, and you close it out. Okay, and it's this set that I want to compute for different families F. So before we start to look at the answer, we should always look at the universal object, which is the universal cover of all my hyperbolic manifolds. And what's the spectrum of the Laplacian on the universal cover? And this will be very important because if I go to one forms or co-exact one forms, something fundamentally different occurs here. So when you look at the hyperbolic space, you insist on not looking at just eigenfunctions of the Laplacian without any boundary conditions. If you insist on making it the L2 eigenfunctions, so you close with respect to compact support when you define the spectrum, then all of a sudden 0 is not in the spectrum. And this is well known to many people, certainly to Selberg and Harishchandra, who worked out the tempered spectrum of globally symmetric spaces. In all cases, and there's a discrete series, which is often very important, and in our picture would be sort of a forced eigenvalue, and we would then remove it in our discussion. All right, so the spectrum starts at a number which is positive, so if D is 2, then there's this famous number 1/4, and if D is 3, this starts at 1. So the spectrum is an interval on the universal cover. And somehow, if as we vary over our family, we converge, and I'll return to this, there's a notion of Binyamini-Schramm converge. If we Binyamini-Schramm converge to the universal cover, then the spectrum is going to at least be as rich as the spectrum of the universal cover. So this interval will be relevant once we start to think about how things rigidify. All right, so I'm going to immediately tell you the theorem that got me into this. This is a theorem of Kravchuk. These are physicists. These guys work in conformal bootstrap. The fellow Mazak was at the Institute for Advanced Study working with Nima and Juan Maldacena, and they said, go show Sarnak this, he might be interested in. And I'm still talking about today, so I'm obviously rather interested in what he had to show me at that moment. He didn't quite describe it this way, but this is what it boiled down to. So his co-workers are Paul and Kravchuk. Mazak is the guy who came and showed me this. And basically what he was telling me is that the base node spectrum of hyperbolic 2 overfolds consists of an interval where he knows exactly, there's a little t there. That little t means, so I learned this, somebody told me Mumford used to put little t means the proof hasn't been written. It still hasn't been written, so, but I'm so confident it's correct that that's capital T now. I'll explain the one technical point that's missing. Anyway, the theorem is that the base node spectrum is an interval and then 4 numbers outside the interval. So that's basically you're saying, what does it, what? That's where the numbers that you assume. Then as he was talking, you sort of start to think, oh, I could see how, but he says, I prove it with one theme. Something called the conformal bootstrap. Boom, gives this. All right, so I hope you appreciate that's a computation like the Markov spectrum. That's the spectrum for hyperbolic 3 manifolds. The guy at the biggest here is the Hurwitz triangle group, as you might have expected. It's got the smallest volume. I look at Lubotsky because he computed volumes in other situations with smallest volume. It's the theorem of Ziegel, that the orbifold with smallest volume is the Hurwitz triangle group. The smaller the thing, maybe the bigger the eigenvalue. So this forces this eigenvalue to be very large. That's its eigenvalue. But notice that as the volume increases, there's the volumes. They should be here. That's the eigenvalue. It's not a monotone function of the volume. It's not a monotone function of the volume at all. Anyway, so these are all arithmetic triangle groups. I don't think that's a coincidence. Arithmetic triangle groups which are in the discrete part of the base node spectrum. What a lovely fact. And then here you have an interval. Let me tell you what that interval is. I'm going to discuss it in more detail in a moment. And in fact, tomorrow there's going to be a lecture by Anshul Advay, which we're adding, who has really understood some deep points about this conformal bootstrap, and he will explain this much further. But let me just explain the strategy to prove this. So first I have to tell you what this interval is. So this interval is as follows. There's a deformation space. All right, so now we have to think about the orbifolds. They are discrete subgroups. Some of them can be deformed and some of them can't be deformed. Some are rigid. The deformation space, if you realize the upper plane divided by gamma as a surface, and you look for holomorphic sections, you look for holomorphic forms of weight 4, that's the cotangent space, the deformation space. If that's 0-dimensional, you're rigid. All these guys are rigid. If they weren't rigid, lambda would move continuously and you wouldn't get a point. So some of them are rigid, some of them are not, and we're going to go through the topological types to see something to do with this in the proof. So there's a particular deformation space, one complex dimension. I'll write down the character variety in a second because it's a Markov space. It's the deformation space of genus 0 surfaces. So when you take the quotient, you get a surface with cone points, where the cone points are 2, 2, 2, and 1, 3. And where you put the cone points has one complex parameter, and that's the deformation space or the Teichmuller space. If you divide the Teichmuller space by the group of motions, you get the moduli space of such hyperbolic orbifolds. And it turns out, and that's the part where there's a little theorem here which essentially is now as proved, that the maximum value on this of lambda 1, so on a continuous space, lambda 1, unlike if you took yesterday, it wasn't yesterday, it was last week, we took the wave equation and decided we'll look at the spectrum of the wave equation on a torus. That's not a continuous function on the torus variable, the smallest thing, because the minimum might be achieved somewhere. But here on a continuous space, the function's continuous, so you have this continuous function. When you go to the boundary of this moduli space, lambda 1 goes to 0. So there's going to be a maximum somewhere, maybe at many points, but it turns out there's a unique maximum. That's what is being proved now. And that unique maximum is at a surface with a specific symmetry, which I'll explain in a minute. And that's this value here. And there's also one other arithmetic triangle group which gives exactly the same value because it's commensurable with a common cover. So if you don't like that theorem, you probably should walk out. But that's a theorem which is proved by some new idea. It's the base node spectrum when you go over all hyperbolic orbitals. And unfortunately, we can't rotate this. So you'll have to do this, sorry, to make all you turn your necks. Yeah.
I have a question. You mentioned
Yeah.
just
Yeah.
slide. You said if you go to the
Boundary.
boundary, the lambda 1.
If there's a separating curve, yeah, this is well understood when lambda 1 goes to 0, but it'll at least go down to a quarter. And by that point, there are all sorts of other deformation spaces which are all under this rug of that interval, which are already covering all that. So you see this theorem is very clever because all the interesting stuff is, I mean, where's the number quarter here? It's all underneath this one guy that's covered everybody up. If you've ever seen Bloch wave theory and the idea of bands and gaps in solid state physics, the gaps, that's exactly what happens. They're bands and gaps, and if you want to make a gap, you really have to keep all these bands away from each other. And that's what's happening. Sorry, these are these, and here's the area. I knew I had the area somewhere. You just said it's not monotonically increasing the area.
Yeah. 2, 3, 6, and 3, 3, 4, they have exactly the same eigenvalue.
Yeah,
because
because
they coincide to the third point.
Exactly. That's why that point, yes. This is exact. This point is double multiplicity 2. Yeah. Yeah.
The 2223 type molar space gives you the entire array from 50
Yes.
to 2?
Yeah, yeah. That's the decisive particular thing that covers everybody else up. Yeah. Okay, so let me say words about the proof because I want to explain where the new idea is. Because most of this, if somebody told you this was true, you would go and start doing this yourself, and then there's going to be a new idea. So you have this signature of these hyperbolic orbifolds. There's the genus of the surface, and there's the order of the cone points. And you have this Teichmuller space. It's finite dimensional, and its cotangent space is given by Riemann rock. So you can compute this, and this is very important. In this conformal bootstrap, we're going to input topological information, which is something you do know, while eigenvalues you don't know. So the deformation space you know, and there'll be other things that you also know. So this is this Teichmuller space that we were just discussing, and I'll give you its parameters in a second. It's one complex dimension, and it turns out there's a unique point inside this moduli in this Teichmuller space, which is fixed by the mapping class group, and it's order 3. So there's a symmetry at this point of order 3, and it's only this that's going to allow us to prove this theorem. I want to explain why. Well, I've got it here. Who of you know that? I know Zeb knows this. Suppose we check the zeros of the Riemann zeta function up to about 10 to the 20, and they're all on the line. If there was a multiple 0, we would not, in this world, at this point, know how to deal with that. If there were multiple 0, we'd never be able to tell whether the two zeros are on the line or just slightly off by a finite calculation. As Selberg once taught me, you can show with a computer whether a number is not 0, but not that it's 0. So this is a very serious issue. I'm saying that the maximum of the lambda 1 on this moduli space is at the surface. And I'm going to prove it numerically, because we don't know how to compute it any other way. We're going to see a bootstrap in a second. So how can you compute that number and be 100% sure? Well, if I have a function on the plane which has a symmetry of order 3, and it's a real valued function, and it's smooth, then the first derivative must be 0. So it's a critical point. And once it's a critical point, I know that I have a chance now, as long as the Hessian is pointing me one way, then I can rigorously prove I'm actually at the maximum. And that is being done as we speak. We know how to do it now. And that's
You can local, so it's a local maximum, right? You need to have some.
yeah. Now, local to global, so then there's a neighborhood you remove, and then this is very true, this thing. So for a physicist, it would be a complete triviality. You just check it at different points and say, yeah, it's a maximum here. But I'm saying, how can you be 100% sure that you are exactly a maximum there? So physicists would check the Riemann hypothesis, and the zeros are, yeah, they're close to the line, so they're on the line. But if you really got to a 0, which was a double 0, you'd be stuck. And if this wasn't there, we wouldn't know how to complete this program. But this is not an issue. So there's this maximum, and that's the endpoint of that interval, and that So the proof obviously has to say that if you're not in this moduli space, then you know something about the topology of the space, or you know something so as to look at just a finite list. And that's what's done. All right, that's the moduli space. I couldn't resist it because it's a Markov. If you write it in terms of traces, it's a Markov equation, and the point that's got the symmetry is this point where they're all equal, which is fixed by the symmetry. Just so that I have a love affair with Markov, as some of you may know. All right, so that what they show, Mazak et al., is that if lambda 1 is bigger than 15.7, so the number, that endpoint of the interval is 15.790. So if you're bigger than some number slightly less here, then they're going to show you one of these, or you are in that moduli space at the endpoint. That's what the theorem is going to, that's how it's going to proceed.
That is the theorem of the capital T?
Sorry?
That theorem is with the capital T?
That theorem is with a capital T. The one with a little t is this maximum. Exactly. That is pure thought with some calculation which is completely reliable. All right. So the thing is that if lambda 1 is bigger than 15.7, then X is in a very small set of signature types. And they are those about 5 triangle groups, which are rigid, and the only other one possible is this one deformation space. So they use some standard inequalities. There's this beautiful theorem of Yang and Yao from many, many years ago, which estimates lambda 1 using gonality. So if I have a curve with a complex number which has a certain gonality, that means it's the least branched cover of the plane, and you put that branched cover into the lambda 1, into the Rayleigh quotient, you can estimate that and get bounds for upper bounds. All these are upper bounds for lambda 1, which depend only on the topology, on the gonality. So you can use that to immediately move away from many, many different moduli, signature types, but not all. And the novel idea comes from something completely new. It's called the conformal bootstrap of, highlighted this thing by Polyakov, called the crossing equation. So there's this conformal field theory, which is supposed to be a conformal field theory. It's got a conformal group acting on it. And it's supposed to give you correlation functions for certain statistical physics, especially three-dimensional Ising problem. And in this theory, they postulate that these correlation functions satisfy various operator expansions. So you write down some axioms. And in that theory, there are unknown numbers called the spectrum of the conformal field theory. So if you imagine like with the Gaussian, all you need to know is the mean and the variance. In this conformal field theory, you have to know an infinite set of data called the spectrum of the conformal field theory. And they don't know how to construct these. This is why we have stuck, why they are stuck in the real physical problem. So there's the theory, and a big change occurred when people started to use this thing called the bootstrap. So what this bootstrap is you assume you have the theory with some parameters, and you write down these expansions in 2 different ways, and you get consistency conditions called crossing equations, which are explicit infinite set of equations that the parameters must satisfy. And then you don't know how to satisfy these equations, but you take some subset of those, cleverly chosen, and you try to run numerics to see if they're solutions, and you get bounds. One of the great achievements of this theory, which is begging for mathematics, is that they can do this is Polyakov and I think Zamolodchikov. There's after you do these numerics, so that's the numerical conformal bootstrap, they get bounds for the critical phenomena which are within 1% of what physics tells you with a critical phenomenon. So nothing is proved there, but there's something obviously correct about this theory. So that's what this Mazak and co work in. It's called the conformal bootstrap, and they decided to apply this kind of philosophy in a conformal field theory, baby conformal field theory, which is the following. So this is a unitary one, so it's not a physical one, but the methods are all the same, and Advay will explain tomorrow what these equations are. These crossing equations are going to give you a set of equations, and this, of course, is of great interest to me. So they're going to apply this philosophy of working out with these crossing consistency conditions are for correlation functions. Always only 4-point correlation functions that you expand in 2 different ways. I'll tell you what they are here in a minute. And the data associated with computing these crossing in the case of functions, so we look at the algebra of functions on PSL2R on our orbifold, involves A, the spectrum, that's what we're interested in, that's transcendental. B, the holomorphic forms of weight K. This is what's going to distinguish, for example, the Hurwitz triangle group from everybody else. It's got the biggest K, for which there are no holomorphic forms of small weight until it has to, of course, once K gets large, you will always have sections, but that's what distinguishes it from the rest, and each of those that are peeled off are through this topological invariant, which is the minimal K such that there's a holomorphic section. So the data from these crossing equations involves this, and triple products. So you write down these correlation functions. They're given, by the way, in physics, if you see this, means expected value. Diamond of anything inside, if these expectations are computed explicitly here in terms of this, and these numbers C, J1, J2, J3, which are the integral of triple products on the homogeneous space. And the equations are a system of infinite system of equations in this. They're quite simple, but they're nonlinear. And you can try use them to estimate the parameters. In this case would be the eigenvalues here, or these numbers. And that's what this bootstrap is in this case. And they put this in some, they choose these judiciously. And then they actually run a linear program. I'll get back to that. And they conclude that if you are not if you're not inside that one moduli space and lambda 1, in other words, the bound they get is so good that if you're bigger than 50, they give upper bounds. So if you're bigger than 15.7, you're in one of these finite linear types, and then you can just check what those eigenvalues are, and that's a theorem. All right, so Adve has proved a fantastic converse to this theorem. So he will speak about this tomorrow, that those equations, so they always want to know that these crossing equations are equivalent to the field theory, and in this case he's able to prove it by a really unusually new thing. That if you take the axioms, he will show there is a gamma, there is an orbifold such that the spectrum is coming from the axioms of the conformal field theory. This baby conformal field theory. So he'll explain that tomorrow. I explained what was special about the Hurwitz group. Not only does the upper bound they get for the Hurwitz group, lambda 1, it computes it without, it never inputs gamma. It only inputs that data and makes estimates and runs a linear program. It gets the Hurwitz triangle group eigenvalue to I think 8 decimal places. And at the beginning he was telling me that it's going to actually compute it exactly if you just run the linear programs further. Then he changed his mind. Anyway, for the purpose here, you don't need that to more than 2 decimal places to move down.
What would that mean to compute it exactly?
I'm about to explain to you. So there's a great theorem of Vyazovska that they have a new proof of. Okay, so I go off on tangents, but I've got 3 lectures, so I should. Let me answer your question. That's this comment down here. Hartmann, Mazak, and Rastelli have a beautiful paper explaining Vyazovska's work and explaining that her magic function that she constructs brilliantly out of nowhere, she's motivated and looked like integrals, she just writes down an extremal function, is contained in their work after seeing and making a transformation. It's a simple rational function in their theory. So let me just say a word about that. So there's a very similar story. So the question is whether lambda 1 would saturate. Does this linear program determine lambda 1? And the answer is now he doesn't think so. But there's another problem where there was exactly the story in the geometry of numbers about sphere packing in dimension 8 and 24. And there's a linear program that you can write. It's called the Cohen-Elkes linear program. It was actually discovered before them by Gorbachev. I don't think he's Mr. Gorbachev. His name's Gorbachev. Anyway, they're the first to run the linear program. It's a beautiful thing. You run the linear program, and they found that in dimension 8, so linear program is just a spherical Fourier transform. Linear program about infinite dimensional about a function and its Fourier transform and some relation between f and f hat subject to linear constraints. And that linear program, if you run it, by the construction of Elke's cone gives you a bound, upper bound for the density. And the more you run it, the more it is exactly what the Leech lattice gives. So it became clear that this, and only in dimension 8 and 24, and dimension 2. But 8 and 24 were unknown, and this was a big, big unsolved problem. So you run this, but they could not show that. So you have to show there that this the extremal for this infinite dimensional linear program is the number that is given by the Leech lattice, which has got the lattice inside it. And Wiesowska wrote down a function which proves that. That's her magic function. Okay? Their linear programs are very similar, and they found a transformation from certain conformal field theories that are called chiral to the Elke's linear programs. And they're the same. This transformation they found is very complicated, but in their coordinates, her magic function is very simple. So they give a new proof of the fact that that actually computes the density and solves this sphere packing problem. They did it after her. They're taking nothing away from it. They're interpreting it, but it was a natural thing that Mazak was doing anyway, and Hodden. Okay, so I will leave for Advait to say more about the actual converse here, which I think is the first theoretical study of these crossing equations in a very simple situation. I want to emphasize the conclusion of his theorem. I've never seen a theorem. I've seen many theorems, but I'm not familiar with a theorem where the endpoint is, and this topological space is SL to R over gamma. He reconstructs gamma out of the equations. Okay, so he will talk about it. And it was a conjecture of Mazak that he's proving. All right, so now that we have the base note spectrum on all hyperbolic orbifolds, that's the end of the story, let's take a subset. An obvious subset that I can't resist. And of course, I started making these conjectures, and some of them are now almost solved. Yeah.
You go back to the non-arithmetic things. If you tie your hand behind your back and say you're not allowed to use this special moduli space,
Yeah.
can you still ask what is the base notes for this other family?
So you want, what's your subset precisely?
So remove
That one guy. Oh, yeah. Then there's that 2.7. There's another. There are these all these bands that come smaller and smaller, and they will go down to a quarter. We'll see that in a second. The number quarters, obviously, it's going to come up immediately. So suppose instead of allowing all orbifolds, I insist on only arithmetic ones. So arithmetic are ones defined by number theory or commensurable to ones. They're still very rich and much richer than congruence. And that's going to be very important because the answer is going to depend on that. All right, so I'm allowing all arithmetic ones, and I'm asking what's the base note of the arithmetic hyperbolic surfaces? So you now ask what lambda ones can you hit with arithmetic guys? And ever since I've known Alex, we would conjecture this immediately. Firstly, there's a countable set. And there's only finitely many in each of these moduli spaces, so the volume has to get large. So it's a countable set. So we have to take the closure. And as you, I'm sure, guessing, the topology, the volume has to start to grow, so we're not going to have this one guy that sweeps everybody under the rug. So the conjecture is, and it's almost, part of it's already proved, is that there are, so remember when I gave you the spectrum, the Markov spectrum, there were infinite number of points above a certain point. So the conjecture is there are infinitely many hyperbolic, compact hyperbolic orbifolds where lambda 1 bigger than a quarter. It's a hard question. And then every point here is a limit point. Okay? So that's the conjecture of what the base note spectrum for arithmetic is. The discrete part, and I add infinite, and I'll tell you what we know. We know all but this part, actually, right now. So the base note spectrum, the discrete part, is infinite above a quarter, and every point here is a limit point of lambda 1. But through congruence, through arithmetic.
But about a quarter, you know that this is a discrete subform.
That we know. I'm about to prove that to you. For all I know, there are only finitely many, but I'm sure there are infinitely many, but I don't know how to prove it. I know how to prove it if I assume all sorts of conjectures.
But you have commensurable and you have...
This is arithmetic. The next one, so that we're not rigid yet, we'll be rigid in a moment. That's why I'm so interested in rigidity. Rigidity will be Selberg's conjecture, of course. Okay, a lot is known towards this. So firstly, let me answer your question. This is the analog of Alon-Bopana. It was well known to Huber many, many years ago. If you have hyperbolic orbifolds whose volume goes to infinity, area goes to infinity, lambda 1 must go down to at least a quarter, if not lower. So the lim sub is a quarter. And you just put a test function in the trace formula, and the coefficient in the trace formula just straight, things are positive, and you just put inequalities. This was Huber did, and you learn this. And the main term is the volume term in the trace formula, and the volume goes to infinity, so you get this fact. So this is saying that the spectrum above a quarter is discrete if the volume goes to infinity. On the other hand, if you're arithmetic, then this Borel-Prasad theorem says that there are only finitely many arithmetic groups whose volume is less, area is less than a given number, so the volume has to go to infinity if I have an infinite sequence. So that proves that it's discrete above a quarter. Now, how to make limit points here? So, of course, if you assume Selberg's conjecture, which I'll return to, then of course we'll have a quarter as a limit point, but we don't know Selberg's conjecture. So it was quite remarkable when Maggie and his student Hyde, a couple of years ago, proved that 1/4 is a limit point. They found a proof that 1/4 is a limit point, which is a similar thing to what Friedman proved in the graph case, that there are hyperbolic, and I'll tell you what the real theorem is. They start off with any hyperbolic orbifold, and they look at the random n-sheeted cover. So if that guy's starting point's arithmetic, then everybody's arithmetic in this tower. That's why we're going to do it in the arithmetic thing. And then they prove that there is a random guy who's lambda 1. We know it has to go down to a quarter, but if you give yourself an epsilon, they can make the lim inf greater than or equal to a quarter minus epsilon, so epsilon disappears into the lim inf. So the lim inf is the minimum of lambda 1 of what you started off with, which is certainly going to be in the spectrum, and a quarter. And so if you start off with somebody which satisfies Selberg, which you can do by numerically finding one or take the modular group, it's easy to show it satisfies it, then this will be a quarter, and that puts a quarter in the limit spectrum of the base note. And then Maggie went even further and adapted an argument of, in the graph case, which I'll mention in the third lecture due to Fan Wei and Nogalon, he adapted it non-trivially to show that whole interval 0/4 is a limit point. I repeat, every number in a 0/4 can be realized as the limit of lambda 1s of arithmetic manifolds. Again, by random covers and then a local change. So the conjecture is all but proved except for the fact that there should be infinitely many points above, which to me is very attractive because that was what Markov gave us in the Markov spectrum. So that is very hard. That's already like on the other side of a quarter. All right, so that's what we know about this. And it was in this context that I was giving these Chern lectures when I wanted to talk about this breakthrough and the breakthrough by Mazak that I just decided that this is an interesting problem and one to explore.
Why do you think it's interesting?
I'll get back to that in a second. Firstly, in the graph case, I've got now 3 proofs it's infinite. And I'm going to mention next time, so there's an analog in the graph case, 3 proof of super Ramanujan graphs, 3 different proofs. One, it comes from number theory. Here, we don't have any of these other methods, and there's a number theoretic conjecture, which I'll say in a minute, which would imply. Okay. All right, so the base note spectrum for congruent surfaces, this is where things rigidify. Obviously, I'm now looking at more and more special hyperbolic surfaces. And this is where I started, and this is where Alex started. This is Selberg's conjecture that the base note spectrum of congruence is a quarter. Quarter can actually occur, infinite multiplicity. And I put plus epsilon. This is exactly, Selberg didn't conjecture there's anybody above a quarter, but I claim they're infinitely many. All right, why do I believe that? The analog in the discrete world is true, and 3 proofs give it. In this case, if we assume Selberg, So it's very hard here because we don't even know that you can stay above a quarter. I mean, the best we know is the theorem of Kim and myself, extended to all these groups by Brumley, non-trivial. Kim and my proof depends on my work with Zev and Dua. That's the best we know, so that's this number. It's quite close to a quarter, but it's not equal to a quarter. But that's the best that mankind knows at this point. So why do I put plus epsilon? Because I'm saying there are infinitely many here. Now, Langland's, towards the end of his writing, started to say that part of his conjectures are the fact that if you, so the eigenvalue of quarter appears. And you realize how clever Selberg is that he didn't say lambda 1 was bigger than a quarter. He put greater than or equal to a quarter. Turns out there are many which have eigenvalue a quarter, and those are special Galois representations. So one reason that the theory of automorphic forms has...
He must have known this because massive.
I'm not so sure. He would never say what he knew. Yeah, but he put greater than or equal to a quarter. There are theta lifts, this is true. So there's these conjectures of Langland's. Langland started to add, and I was very surprised, the converse, that the only reason you have eigenvalue a quarter is because of Galois representations. This is a transcendental object, but it has algebraic coefficients. I mean, it's got not algebraic coefficients. In the Galois case, they would have algebraic. What?
30 years ago, it would almost be.
No, he's no comment. So, if you believe that the only way you can have eigenvalue a quarter, then I know how to construct compact quotients which do not have this. The Galois representations won't exist, and so then their lambda 1, if Selberg and that statement are true, would have to be bigger than a quarter. Sarah's done this with weight 1 forms, holomorphic forms. He's shown that for gamma naught n, for certain n's, there are no weight 1 cusp forms, where this converse theorem is true.
They're saying if you know that only weight 1 more or less gives you the
If weight 1 corresponds to finite art and Galois representations, then you could actually, that's the epsilon. Yeah. But that's not part of the Langland's program, and I was a bit surprised. Anyway, this part, you asked why I believe it. That's probably true. I'm sure it's true. Now, nobody said you have to construct, in this problem you have to make congruence. It's tough. Nobody said that you have to make these guys with congruence. If you can make them by some random construction, kol hakavod, as you guys say. See, I know. But you will see this with the graphs. There are ways to do this, and there's something really interesting that happened just last week. You'll hear about it on Thursday. Yeah?
Suppose that the eigenvalues come from a Hecke eigenfunction. Do you know that when the Laplacian eigenvalue is a quarter, then the Hecke eigenvalue would be exactly 2 square root p?
No. No, I don't know anything about something that's got eigenvalue a quarter. I can't say anything more. It's like maybe there's an accidental form with eigenvalue a quarter. All right. So that is the Laplacian base note spectrum on surfaces, and I'm going to go to hyperbolic 3 manifolds, but just let me give you one that goes back to Riemann. Riemann was very interested in the holomorphic spinors, or the number of sections of the square root of the canonical class. Having understood how many sections the canonical class has, he asked, and he proved a fantastic vanishing theorem, which is beautifully described in this book of Farkas and Kraft, beautifully described the vanishing theorem of Riemann. So it's not a topological fact. The dimension of the space of holomorphic spinors, if you want, or harmonic spinors, is not a topological invariant. So you could ask about the Laplacian, which corresponds to the Dirac operator in the setting. So this is weight 1, or the square root of the canonical class. And the first thing you should note is that the spectrum on the universal cover on holomorphic spinors is not got a gap anymore. So Laplacian is non-negative, but it starts at 0. So now you could ask, what's the base note spectrum? So now I'm going from PSL to R to SL to R because I'm choosing a spin structure. And I'm asking, what is the lambda 1 spectrum on the bottom? And you've got to ask this question, and it has a nice answer. We don't know, but we do know that it's not rigid. You can make limit points. It's kind of surprising. So this is the theorem of Adve and Giri. So a lot of these theorems come out of a course I taught. I had such good students, 5 of them went and solved this problem. It's such a pleasure to just have you mumble a question and somebody answers it with really non-trivial argument. So it turns out that, and I'll return to this, they construct examples. They cannot be congruents. You can't Binyamini Shram converge to the upper half plane, or else you would always go down to a quarter. So to make these, they make it through abelian covers using sort of block wave theory with a gap. They're arithmetic examples, very cleverly engineered, which have infinitely many limit points. I just want to point that out because I'm going to go to hyperbolic 3 space where these problems are really natural. All right, so let's start with hyperbolic 3 space. So that was it, my story for hyperbolic plane. For hyperbolic 3 space, there's already Mostow's theorem. Not Mostow, this is known by Fricker probably. And certainly Solberg, that there are uncountably many hyperbolic 3 manifolds. So,
Peter,
yeah.
can I ask about the Dirac operator?
Yeah.
What you said was about the general case, not arithmetic or congruence.
Correct. So they construct arithmetic. Now, let me make clear that if you have the Dirac operator and you have a continuum, then of course you can make limit points because you have an interval. But the minute I say arithmetic, I have uncountably many, and the only way I'm going to make limit points is to make the topology go to infinity, because there are only finitely many in each topological type. So then it's a very natural question. So the answer is that with arithmetic spin structures, arithmetic.
Not the congruence. These are not.
When it comes to congruence, you can't make a gap. I'll get back to that. I'll explain that. There's no gap possible for congruence. Yeah, so the congruence can put a very serious limit on what you can do as far as gaps. All right, so hyperbolic 3 manifolds are countable in number. So you take the closure, and then they're automatically countable. There's no continua, so we immediately get to the beef problem, and that is that the spectrum should be the interval. You should be able to make anything in the 0, 1, and the universal cover number is 1, and there should be infinitely many there. That's a conjecture. That's an obvious conjecture for hyperbolic 3 manifolds. And again, this is discrete. Now here it's a little less obvious. So you can order hyperbolic 3 manifolds by volume. This is a great insight of Jorgensen and Thurston. Because the only way you can make limit points of volumes is by certain Dane filling. And that Dane filling forms a limit point of hyperbolic 3 manifolds, say compact ones converging to one with a cusp. And then you can look at how lambda 1 behaves under this to see whether lambda 1, what can happen. And in fact, Dodgek is the guy who studied this with Chevelle. And using that, you can see that that as you go through the Stein twist, lambda 1 will basically converge to lambda 1 of the limit. Since the limit has a cusp, lambda 1 starts at 1. So you can't, with Dane twists, get any limit point here. And then as the volume goes to infinity, Huber's argument and other arguments work. So the spectrum of hyperbolic 3 manifolds in one infinity, the base node spectrum, is discrete.
This is a spatial results for this specific point.
Yes.
For example, if you go back to the dimension you take on the type molar space.
That's continuous, yeah. Oh, but
lambda 1 of the
is continuous on the space. If you go to the boundary, it'll go typically to 0 or a quarter if there's no separating case.
So this is always true.
This is a special thing about this. He's special about this. About this Dane filling, yeah. Okay, so this is discrete. This argument actually makes one a limit point by not going to infinity, because you can actually start off with lambda 1 greater than equal to 1, which you can arrange. There are some hyperbolic 3 manifolds for which we know that's true. And if you do that, then you'll have 1 as a limit point without having the volume go to infinity. We don't know how to do the Maggie argument. By the way, I should have said what Maggie was using. Oh, it was at the bottom there, and I just got a little too excited. the proof. So, the proof uses a new breakthrough, first by Hoger Up, I think you pronounce it, Ford Johnson, and then also by these two guys who did it in the graph case. So in free probability theory, in random matrix theory, you easily see where most of the eigenvalues lie, but not the fact that we have a gap. So if you want to show that the random cover has some property, you want to say that there's no outliers with probability going to 1. And that breakthrough, that's called strong convergence, comes from this breakthrough in C-star algebras, and the groups, so they can do it for artin right-angle groups, for surface groups, but they can't do it for hyperbolic three-manifold groups, which is why we don't know the result here, uses this strong convergence breakthrough that starts with these works, and there's a lot of activity around strong convergence, a lot of interesting new breakthroughs that have happened. But that's the breakthrough that Maggie and Hyde are using, I should have said. All right, so back to three manifolds. So we can easily make 1 as a limit point by this cheating because of the fact that when you converge this finite volume. The conformal bootstrap, these guys are amazing. These guys will use anything. They went to the census of hyperbolic three manifolds, and they just compute the eigenvalues of anything there. They run their conformal bootstrap. They got some new inequalities. They don't have a theorem as clean as what I gave you for hyperbolic orbifolds. But they did learn one thing that shocked me. I was sure that the hyperbolic three manifold of the smallest orbifold of the smallest volume should give the biggest lambda 1. Not true.
But this was just a straightforward
It is a numerical fact that these guys are shameless.
If you start with the surface and you take all the random covers.
N degree n covers, yeah. So it's all group theory. It's all group
Right. So then the infimum of this, and then the lambda ones of them
those?
give you the original lambda 1 as the limit point.
Or a quarter. If the lambda 1 of the original guy is bigger than a quarter, then it'll give you something greater than equal to a quarter. It can't accumulate.
Yeah, of course.
Yeah,
because
yeah,
it
yeah.
cannot
But
be-
it does the best
No,
it
but
can
you
do.
see, no, but in three manifolds, by now we all know, Eigel and all this, that they've, at least up to finite index subgroups, they map onto a free group, so you can do this rich random theory.
Correct.
Can you,
No,
why
no.
don't you get there,
Yeah.
the limit point?
Because this passage to the free group is not. It's not from a homomorphic image. They need to construct finite covers.
Once you
It doesn't.
fix the finite cover,
Yeah, we'll discuss it. They've tried. They have something slightly weaker that they can do. They can do it for Artin right-angle triangle groups. So this is about combinatorial group theory and strong convergence. They don't know how to do it for hyperbolic geometry. All right, so I just wanted to point this out, that these guys who run this bootstrap also want to compute things. They use the trace formula. They use anything that's available, and there's something rather interesting there. That you might think the guy with the smallest volume, which was a great achievement by Marshall and Martin, that they computed the orbifold, the hyperbolic orbifold of smallest volume, compact, does not produce the biggest lambda 1, which is not true. Slightly rearranged. Okay, so on functions, modulo the fact that we don't know how to do these random arithmetic, or you don't have to say the word arithmetic, we're already in the hyperbolic setting. There's a much more beautiful question. Let's take the Laplacian on one forms. So this, now the kernel of the Laplacian on one forms by Hodge theory will measure the first Betti number. So if I want lambda 1 to be positive, so now we're back in the situation where lambda 1 equals 0 is not automatic. So the base note is going to be not lambda 1, but lambda 0. Because there can be hyperbolic three manifolds which don't have any homology. Infinitely many homology three spheres, hyperbolic. So I'm looking at lambda 0. The base note spectrum will be about lambda 0, not about lambda 1. Different to the case on functions, if you look at the Laplacian of a Laplacian on one forms, it's the interval 0 infinity. Okay, so there's no gap there that has to do with this L2. Everything is tempered in the language of representation. So this now looks like a situation where maybe we have rigidity or not, and this remains open. This is, or is there a sequence of homology 3 spheres, hyperbolic homology 3 spheres, which have a spectral gap on one forms? So this would be like a really spectrally gapped homology 3 sphere. Or is it true that if you have homology 3 spheres whose volume goes to infinity, lambda, is this rigid or not? So this is a question that we don't know the answer to. But there is a very beautiful theory here, and it is connected with the Seiberg-Witten equations, but in an application that's rather unusual. So when you look at the spectrum on one forms, the Hodge theorem breaks up into two parts. There's co-exact forms and there's exact forms, and the spectrum is the union of these two spectra. And if you stick to the co-exact guys, then you can ask about the lambda 1 spectrum for co-exact guys. And Lipnowski and Lin made an amazing observation. They observed by a Bochner kind of argument, integration by parts kind of argument, that the Seiberg-Witten equations on a 3-manifold for which lambda 1 on co-exact 1 forms on a hyperbolic 3-manifold, if that lambda 1 is bigger than the number 2, 2 comes from integration by parts, you need 2 bigger than that, then there are no solutions to the Seiberg-Witten equation. And that's kind of remarkable. And then they said, well, are there any such? They go to the census, and they found 5 or 6. Are there infinitely many? Well, that's our lambda 1 spectrum on co-exact 1 forms. Now, I don't know the importance of the number 2 in this game, but you could ask, does lambda 1 on co-exact 1 forms have to go to 0 as the volume goes to infinity? And the answer is no. Spectrum is not rigid, and this was solved by this set of 5 people. So this is the base node spectrum on co-exact 1 form. So this was raised in this Lipnowski and Lin paper. They produce infinitely many limit points. So at this point in this game, we are only, probably there's an interval there, like in Markov at the bottom. We don't know anything as good as that, but when we make limit points, we say it's not rigid and we feel we've made good progress. So it means they're making a sequence of hyperbolic 3 manifolds, homology 3 spheres they can make. They can't be congruents, they can't come from number theories, I'll explain in a second. They have to be coming from some very weird limit. And they have the smallest eigenvalue not go to 0 on co-exact 1 forms. On the other hand, they do prove rigidity, so they understand this well enough in terms of tame geometry, that if you restrict the number of generators of pi 1 in your family, then you can't do that anymore. So the base node spectrum on integral homology spheres at pi 1 bounded by n is rigid. There's infinitely many of those, and lambda 1 has to go to 0. So this is work of Amina, her name is Abdul Rahman. She's a student of Akshay, Advay, Giri, Lowe, and Jean, all of who are in this class and answer these questions beautifully. It's a beautiful paper now, I highly recommend it. All right, so I'll end by talking about rigidity and the question that Alex asked me immediately, what about higher rank? What's the relation between Morgulus rigidity or superrigidity and this rigidity? And there's obviously a great relation. And the reason is the following. So firstly, suppose I have a sequence of locally symmetric spaces or locally uniform geometries. I'll say everybody says they Binyamini Shram converge to the universal space if the following is true. You don't demand the much harsher condition that every ball looks like the universal cover, but only that most balls look like the universal cover. That's the key relaxation there, which makes things very general. So let me repeat. Most balls in the quotient of larger and larger radius will eventually look like the universal cover. Now, if you Binyamini Shram converge to the universal cover, then it's a very easy exercise that the spectra, any spectra that you're looking at, will be at least as rich as the universal cover. So if the universal cover is got spectrum 0 infinity on 1 forms, all these guys are going to not be able to, they won't be able to keep a gap. You can't create a gap if the universal cover doesn't have a gap. So we're going to immediately be, the question what's happening in the universal cover is decisive. If we Binyamini Shram converge. And now to answer, I think, your question, there's this beautiful theorem of Freitschek which Erez Lapid and Finis proved if you go through towers of a group, but he proved this as you go over all congruence groups with changing the definition of the congruence group, completely uniform. So in 2 and 3, hyperbolic 2 and 3 dimensions, every sequence of hyperbolic congruence groups converges Binyamini-Shrum, no matter how you make it can't help itself, it must converge to that universal cover. So with those you can never make a gap for harmonic one forms or for spinors. It's a consequence. So this is a beautiful theorem, and that's a consequence. So a question that we asked about hyperbolic 3 manifolds, number theory has nothing to do with it. It's in fact the opposite of number theory. So this is a kind of rigidity which rigidifies the spectrum. And if you go to higher rank, there's this theorem that the authors call themselves the seventh samurai, so I will call them the seventh samurai. Eber, Bergeron, Bringer, Gerlander, Nikolov, Rumboldt, and Semmet, Gerlander, of course, is the following, that if you're in higher rank, then you automatically, Binyamini-Shrum, converge to the universal cover. That means that this problem of the spectral gap is only a problem about what's happening for congruence groups. There's also that arithmeticity. And the only gaps you can't make gaps, you automatically can't make gaps inside where the Plancherel measure is supported. And you'll never make gaps in there. And whether that's everything supported in where the Plancherel is supported, that's the Ramanujan conjecture. So we understand very clearly there's nothing new to say in this situation because of this theorem. So this theorem only exists when you can make weird covers, or if you're trying to prove Selberg, which is about lambda 1. So this high rigidity I find to be, this is not something you would ask. Margulis sort of closed the subject, and these guys further closed it with this. That's pure number theory. Hyperbolic plane and hyperbolic surfaces, they're kind of rich. Now it's very interesting that the 4 guys in Mazak's theorem that lie outside there are arithmetic, and there's some interesting thoughts as to maybe whether it's true connected with this linear program in saturation. I'll stop here. Thank you. I have a lot of references. And I urge you to listen to Advait tomorrow, because I did not do justice to this field theory, and there's something really novel and new there, that you can compute the eigenvalues of a hyperbolic surface by writing down an infinite number of equations involving the lambdas, the holomorphic forms, and the triple products. And they are equivalent to computing the eigenvalue, all the eigenvalues. And that's what's being used there. Yeah?
Yeah, I have a question on a different direction. What happens if you contort a little bit your geometry? What happens with the spectrum information?
Yeah, so I'm working with a rigid geometry because if you perturb it a little bit, everything will move a little bit if it's a elliptic operator, and things are continuous in perturbation. So if you have a spectrum that's discrete below the continuum, then things will move continuously, and then making sense of a particular number like a quarter is meaningless because you can perturb it. So in that sense, this is why the whole title of these lectures are locally uniform geometries. The geometry has to be like constant curvature. It's something to do with group theory and symmetry.
But eigenvalues are not isolated.
Okay. Now, if you're in a situation where you're in the continuous spectrum, this is a lovely question. Do these dissolve into resonances? These are very hard questions, and in this case, they're very relevant. So if you were in a hyperbolic surface and you're asked about perturbing, even within the deformation space, an eigenvalue which is square integral in the continuum, which exists, do they become resonances? The answer is yes. This is work of Phillips and myself and many things else. One can be misled there quite easily as to what's true. Zeb is looking, say no more.